All right, so let's go ahead and now we're going to work with our voltage divider circuit in order to, again, correlate strain to, it doesn't matter what direction, to some change in voltage. So voltage divider circuit, we can kind of see a schematic of it here. We have some input voltage or excitation voltage, just depends on kind of the parameter. V naught is essentially what you're measuring. So you are measuring, there's two resistors that are in parallel. So if there is no voltage being pulled here, then if I want to describe essentially this circuit and the voltage and current relationships, it is just going to be, as I kind of go around the circuit, these are in series. So I'm just going to add them. So the equivalent resistance will be this, and then you just plug in and rearrange that expression here. If we are actually pulling some voltage here, then V naught is just equal to the current times R over 2, just this resistance, and we just pull and then substitute this in here. That's it. Not too bad, right? That's it. That's the big, scary voltage divider circuit. So that's essentially the math that you're going to work through. Now, the Wheatstone bridge circuit, really, even though it looks more complicated here, and this is called a full Wheatstone bridge standard configuration. So you have resistor 1, 3, 2, 4, 4 resistance, basically resistors, excuse me. And what we have here, and we can kind of see, they're basically two voltage divider circuits. So there's two of these, right? So we have a voltage divider circuit here, voltage divider circuit here. And we're measuring that voltage here and here. So we have to measure what's that voltage from B to D. That's basically what we're going to be doing. So let's break it down. If I look at basically this V1, we can write out the voltage positions 1 and 2. We can kind of put that here and here. I think there's another kind of a nicer, yeah. We can write out the voltage at 1 and 2. And that is simply going to be, just like we did last time, R2 over R1 plus R2 times that V initial. If we are pulling some voltage essentially from here, this V naught, V2 is just going to be R4 times R3 over R4. So that's basically all we've got. You can kind of see the same thing here. So that's the voltage across from there. If we are at balance, V1 is going to be equal to V2. And what you'll find is, if you go through essentially the math and you kind of rearrange this expression, you'll end up with this relationship for at balance. So R1 over R2 is equal to R3 over R4, or that kind of previous relationship that you see here. So this is if we're at balance. The resistances must be equal to one, or this relationship has to hold effectively at balance. Now we're going to leverage this relationship a little bit later. But now we can actually run through the math and see, well, what is V naught? V naught is just going to be V1 minus V2. And this is all from, Kirchhoff's first law, and all. You can verify a lot of these things. But we can write out that relationship, rearrange some things, and what you end up with is a very cool relationship. If we're at balance, and this is here, your V naught is going to be equal to 0. So you can plug in, and you can kind of prove that that is indeed the case. Now, I kind of said this is a full bridge configuration. It's not really in the standard configuration. But in the standard configuration, it's going to be just a little bit different. And you can have a full bridge configuration will be basically, instead of resistors, you'll have strain gauges in all 4 positions. And when you're basically at balance, this relationship will hold. So if we replaced all the resistors with strain gauges, what's going to happen is we're going to take this relationship that we developed previously, and you can see it's a little bit different because basically the positions, right? So instead of 1, 2, 3, 4, it's 1, 2, 3, 4 here. So the expression changes slightly, but now we're looking at how will the voltage change as the resistance changes, because the resistance is changing now because the resistance changes because we have strain gauges everywhere, right? So this is the most general case when we have the full bridge configuration. So you see how the voltage change as R1 changes, R2 changes, R3 changes, and R4 changes. And again, you can kind of do those partial derivatives, rearrange some expressions, and we also can apply this. This is really important. In a standard configuration for Wheatstone bridges, you're going to typically use, and it kind of makes sense, if you want to be at balance, we need to make sure that all of the resistances, the initial resistances of those strain gauges are equal. If not, then we're not at balance, and we're going to have to... Now, you can still work with a strain gauge in that case, but you're going to have to actually modify the equation significantly because you have to take for account that your not always starting at a 0 voltage in theory, and it gets a little bit messy. So you want to make sure all of your strain gauges have the same resistance, or if you have resistors in combination with strain gauges, that those also have the same resistance. So important to measure that. Now, in reality, there's always, it's really hard to get like a 0 voltage. I mean, you can, but especially when we're working with strain gauges. But we'll get to that in future iterations in the lab setting. We'll talk about all the differences. But you can see here that what you're going to end up with is a function like this. The change in output voltage over the initial excitation or input voltage is just going to be related to change in resistance 1, 2, 3, 4 over 4R. We also can leverage this expression, so we can rewrite it in terms of strain, right? So we're just going to plug this into each of these change of resistances. And what you get is this final beautiful equation. For a full Wheatstone bridge standard configuration, my change in voltage will be equal to that gauge factor, strain in my 1 strain gauge, 2 strain gauge, 3 strain gauge, plus 4 strain gauge. This is really critical. The minus signs are important. And we're going to see some scenarios where you can actually eliminate and basically cancel out some strain that you can measure. So next time, we're going to get into how to leverage this and how to kind of figure out, you can solve for so many different things here. Typically you're measuring the voltage here, and then you're leveraging that to calculate essentially strain. You could substitute if you know what's the loading state. You can solve for loads as well. I mean, it's a really fabulous. It's amazing to how powerful this can be, and kind of this idea of instrumentation and how we can measure some of these values. So we'll see you then next time. Thanks. Bye.